So the point of section 4.4 is to try and get used to your properties of logarithms. It's building you up to get ready for section 4.5, in which we're going to solve logarithmic equations and exponential equations. So even though you could just directly calculate this on Desmos or on your graphic calculator, let's try and do this in a way that actually uses some of our properties. And the way I'll start this is to note for you something that you might not realize about 64, and that is it's a power of 2. So it's actually 2 to the 6th power. So, okay, that's good. Now, I'm actually going to solve this 2 different ways, one of which is I'm going to use the power rule here. That 6 in the exponent here can come out front. I also like to call that the parachute rule. So that would be negative 1/3 times that 6 times log base 2 of 2. So I'll put that 6 here like that. Now this will simplify. So negative 1/3 times 6 gives me negative 2. And now I need to figure out what the log base 2 of 2 is. So let's go back and then remind ourselves what the logarithm was all about. You're asking what power of this, the base, remember Megan Trainor said it? It's all about that base. All right. Anyways, what power of the base gives me 2? 2 to the 1st power. Or in other words, when these things match, the logarithm is just going to be 1. So you'll end up with negative 2. Now that's doing it one way. There's another way that we can do this one. And it's even faster. And it deals with this expression right here. It's kind of a nice property of logs. That when this base and this base match, these two things cancel each other out, and all you're left with is the exponent. So that would equal negative 1/3 times 6, which again is negative 2. Perhaps a better, faster way to do that one, but I did like practicing our power rule. And our power rule is going to be important in the next example as well. So, are we okay with this first one? Looking good there?
Wait, the negative 2 came from multiplying negative 1/3 by 6?
Yes.
Okay.
Yep. All right, so let's try another one. And this one comes directly from your WebAssign homework. Something like this. ln of the ln of e to the 50. Now, if you try to do this directly on your calculator, it probably wouldn't work because this would probably be too big of a number that your calculator just couldn't handle. So what I'm going to do instead is I'm going to take and apply the power rule like I did up here to this thing out in front, or this thing in the exponent. I've got e to some power. So that becomes the ln of e to the 50th. So that exponent comes out in front. I'll write it here in a nice manly shade of pink. ln of e to the 50th. Now even this part might not be really that intuitive. So let me remind you that ln of e is really log base e of e. And we're seeing something like we did with the previous problem. With this previous problem, when I had the same base as, or I was taking the logarithm of something that matched my base, that canceled out to a 1. It's going to cancel out to a 1 here as well. So this is just a 1. Nice. So what you're left with is the ln of e to the 50th. Okay, well, that's really the log base e of e to the 50. And now you're using your properties again, where you've got the log of a base of, matching some base to a power. Basically, what's going to happen is you're going to end up getting this. these two things are going to cancel each other out. You're just going to be left with 50. Now you could do that the same way we did in our first attempt at problem A. That is, you can bring that out and say, oh, log base e of e is 1. 50 times 1 is 50. But probably a good thing to know and recognize is this right here. Log ln of e is 1. So it's not a bad idea to keep that in mind here. So if you get nothing else from this little bonus section, that's a good thing to be aware of. Now,
So what rule allows you to put, I went from ln e to the 50 to log e squared to the 50?
you mean this step right here?
Yeah, I'm just confused with how it goes.
Sure.
from e and
So there's really a couple rules that are kind of like that together that really work with inverses. So if you have log base b of b to the y power, for instance, then that's just going to be y. These operations, in effect, cancel each other out. In fact, I can kind of show that to you this way. So if we look at the proof would look like this. We'll start out with log base b of b to the y power. And from there, I'm going to use my little parachute rule, bring the y out in front. So it'll be y times a log base b of b. So my question to you is, what power of b gives you b? And the answer would be the first power. So you just get y times 1, which is y. Now in a similar fashion to this, you also have b to the log base b of y equals y. So they're both expressing the fact that you have two functions that are inverses of each other. It'd just be like putting together, for instance, the cube root and x cubed. Cube root of x cubed. Well, if I cube something and then take its cube root, I get back to where I started. And that's what happens when you do the log and then the exponential of the same base. All right? So appreciate the question. Thank you. Let's see. Just kind of a fun little side fact about logarithms. They do give you some information in kind of an interesting and unexpected way. And let me show that to you with, let's see, do I have it here? No. Let's see. Right here. Yeah, right here. If you take a look at these numbers, the first one's 2 digits, the second one's 3 digits, 4, 5, 6, etc. You can figure out how long a number is in terms of its digits by looking at the logarithm. So when you take a look at the logarithms of all these numbers, if you just look at this leading part, the integer part, and then add 1, that'll tell you how many digits there are. So for instance, log of 121, that's 2 something. If you just take a look at the 2 and add 1 to that, you know you got a 3-digit number. So what's the application of that? Well, it's something that I thought about when I was in college, because in college, and still to this day, they're fascinated by the largest prime numbers. So in this case, they're a Mersenne prime number named after a 16th and 17th century monk named Mersenne. He's kind of like the Facebook of his day. He kept everyone in touch. He was a hub for communications and discoveries and the latest things in science and math. And prime numbers of this form, 2 to some big number power, some prime number power minus 1, those are Mersenne primes. There's only 51 of them known. The question is, how big is 2 to the 82,589,933 minus 1? How many digits long is a number like that? So, good question. And the way we can figure it out is we can take the log of that number. Well, unfortunately, if you try to take the log of this number, it's going to be too big for your calculator. But let me note something for you. This number, and if I don't subtract the 1, are going to be about the same size. So let's just take a look at the log of 2 to the 82,589,933. If I take the integer part of this and then add 1, then I can figure out how long this number is. So because this number right here is too big for my calculator to handle, I'll be clever and use the properties of logs. 82,589,933 times log of 2 should tell me how many digits are in this number. Well, the integer part plus 1. Let's see. You know what? I think I'll just do it in decimals. So we'll shut this one off and do 589933 times a log of 2. So wow. So 24,561,018 digits long. That's a really long number. So it's amazingly big for a prime number. There's a lot of work that goes into searching those and looking those. Prime numbers are what help keep your information secure when you're working on the internet. But that's a story for a different time. Let me get back to the problems at hand, though. That would be stuff like example C here. Example C, log of z to the 9th over the square root, let's do the cube root, of 7x squared. You can't take the 9 out in front just yet. That's because this doesn't apply to the whole thing. So, all right. Then what? Log of z to the 9th minus log of the cube root of 7x squared, like that. Now in this next step, I'm going to do two things. The first one is that I'm going to bring the 9 out in front, 9 log of z. The second one is I'm going to rewrite this. I'm going to write it as the log of 7x cubed to the 1/3 power. Now I can use the exponents here, or rules for exponents. But I got a question here. Yeah, William?
Isn't it 7x squared to the 1/3 power?
Oh, yeah, I'm sorry. Yeah, there should be a 7x squared. My bad. 7x squared. Thank you. Let's make that look a little bit better. All right. So the 1/3 can come out in front, and that'll give me 9 log of z minus 1/3 log of 7x squared. Now I always make kind of a big point of this, but it's because it's a common mistake. This often gets rewritten like this: 9 log of 7 minus 1/3 log of 7 plus log of x squared. That's wrong. Where's my mistake in this? You can. We can use the product rule. So that's what we did here. We had this times this. So the log of a product becomes the sum of the logs. So we're okay there. But there is still something wrong. And I can kind of demonstrate that if I put in some parentheses here and here. So this is correct now, because that negative 1/3 has to distribute itself to both of these terms. And by having parentheses, it does. Without the parentheses, I just have negative 1/3 times the 7, but not times this. So you can write it with or without parentheses. It's up to you. To finish this off, so you're going to have log of z plus 2 log of x, like that. And you can distribute the negative 1/3 or not, but if you do, that's great. If you don't, that's great too. If you don't, just make sure you have parentheses around this. So if you distribute it, 9 log of z minus 1/3 log of 7 minus 2/3 log of x.
What does that want you to distribute?
I don't think that they really care. As long as you've used the power rule, the quotient rule, and the product rule as much as possible. That's what they're looking for. All right, so yeah, thanks for that question. All right, one last one, kind of in the same spirit. Maybe two. So example D. Ln of the square root of x squared plus 9. A lot of times I'll get stuff like this. People will say, oh, well, that's just the log base e of x plus 3. That is, they'll take the square root of x squared plus 9 as x plus 3. That's wrong. You just can't do that. You can't split up a square root of a sum into the sum of the square roots. It's just not true. So what can you do here? Well, what you can do, and I don't have to write ln as log base e, there's no advantage to that in this problem, is write this with exponents. What exponent goes with the square root? Nope. But I appreciate the effort. 1/2. So something to the 1/2 power is a square root. Cube root is to the 1/3 power. Now the exponent comes out front. I get 1/2 ln of x squared plus 9. I'm afraid that's it. That's all you can do with that one. As kind of a fun little last example, a lot of times you're asked to go the other way. Instead of starting out with something like this and turning into the sum and product of logs, you're asked to go the other way. So in this direction, you're asked to what's called expand. And let me show you what you would get in decimal or in WebAssign. You get something like this: expand the log. Now, one possible answer is this. It's the wrong answer, but it's kind of a funny answer. So keep in mind your directions are to expand the log. Here you go. Expand the log. Dun-dun, dun-dun.
You did the same thing in the video.
Yeah. All right. Sorry about that. All right, I guess I'm using my material again.
We did that on the exam. We didn't know what to do. Would you give us like at least 1 point?
It depends how generous I'm feeling at the time, but yeah, sometimes I do give a point for something like that. But in going the opposite of expand the logarithm, let's take a look at log of b plus log of o plus log of o again plus log of k. So when you have the sum of logs, that turns into the log of the product. So I think I did one like this on the video as well, but here's another one. Can anyone tell me what this would be the log of? Logbook. Yay. Which actually has an interesting history. They used to keep track of where they were in terms of longitude or latitude by literally dropping a log off the side of the ship and seeing how long it would take to float to the back of the ship. And then distance equals rate times time. That told them how far they were going, how fast they were going, etc. And that book where they kept all that stuff was the log book. So, in any case, I hope that you're comfortable working with stuff like this. 1/3 x, 1/3 log of y, plus 5 log of z. What I would typically do with these is get rid of the leading coefficients. Here I'll take the negative as well as the 1/3 up into the exponents. Log of z to the 5th. And now you can bring all these together as a product. Oh, that should be a negative 1/3. Log of x to the 1/2, y to the negative 1/3, and z to the 5th. On an exam, I would ask that you get rid of the negative exponents. So you could write it like this. Log of x to the 1/2, z to the 5th, over y to the 1/3. You could write this as a square root and a cube root respectively, but that's not necessary to get the problem correct. Cool. All right. Good luck with those. If you have some questions, please reach out.